Hi, it's me, Tim Dodd, the Everyday Astronaut. NASA just announced the lunar landers for the Artemis program, and to everyone's surprise, SpaceX's massive Starship is actually one of the landers that NASA chose alongside Blue Origin and Dynetics proposals. Whoa. And this brings up a lot of questions, some of which we'll answer in my next video. Should NASA just cancel SLS and use Starship and/or other commercial launchers for Artemis, where we're going to dive deep into why NASA isn't just using Starship entirely and why they're only looking to use it as a lunar lander. But today, I think we need to settle a lot of debates here first about these two rockets, and now more than ever, it's time we truly pit them head to head. Because this very well might go down in the history books as some serious irony that these two rockets even exist at the same time. I mean, despite these two vehicles having very similar capabilities, you couldn't come up with two more opposite vehicles with two drastically different engineering philosophies. I mean, one rocket has been meticulously designed and built for years and years by seasoned rocket engineers, and the other is being built in a field in Texas by a patchwork team of space cowboys, some of whom previously built water towers. So today, let's take a look at the history and the progress of Starship and SLS, including the Orion capsule and everything else necessary for the Artemis missions, their design considerations, and lastly, their capabilities. Once we do that, I think we can answer the question, how is it possible that two rockets like SLS and Starship even exist at the same time? Should they exist at the same time? I mean, one is easily the most ambitious rocket ever conceived and actually being worked on, and the other is living in the past. I mean, literally reusing old parts from retired space shuttles. How on earth did we even wind up here? Two of the most powerful rockets ever made going online at roughly the same time. Well, we've got a lot to cover, so let's get started.
3, 2, 1,
That's one small step for man.
contact with a test 1.
Before we get too far into this video, just wanted to give a quick fun shout out to this awesome lunar mission shirt that I'm wearing. At the end of this video, I'll challenge you to find the Easter egg in this shirt. We'll talk more about that later at the end. Okay, have you ever spent 2 months researching, shooting, editing, and animating a video only to get it completely done and then find out the day before you were planning to release it that every single bit of your video needs to be blown up and you need to reassemble the scraps? Oh yeah, no, I have no idea what that's like. If you're one of my Patreon supporters, you're probably laughing right now at how different this video is from just what you saw earlier this week, which I'll keep up in there in Patreon just for posterity's sake. So please forgive me if you can tell that I've shot this video in pieces, because I have. But there's a lot of good info in here that we need to get to you, because you guys know me. Once I got into the topic of SLS versus Starship, I maybe got a little too carried away answering my own questions, diving in deep, and correcting a lot of assumptions that, quite frankly, I had wrong. But I've boiled this topic all the way down, and we're going to cover all the bases in great depth, because this one is nuts, and you guys debate this all the time, so we have a lot to settle. Now, because we've got so much to cover, and just like all my long videos, here's the timestamps if you need a reference for later. But seriously, don't skip through this video. You'll be shocked at some of the things that I learned, at least about the history and the progress, and of course, some of the conclusions as well. And I've got quick links to these topics and an article version of this video in the description too. Okay, right off the bat, we've got to make one thing clear. NASA and SpaceX are not competitors. If you love SpaceX, you can thank NASA for that. NASA is SpaceX's biggest customer and their biggest supporter, so let's keep that in mind. As if that wasn't obvious now that NASA is literally investing in Starship for the Artemis program and seeing NASA plastered all over SpaceX's Falcon 9 rocket for the commercial crew program, the relationship with NASA and SpaceX goes back to pretty much the beginning of SpaceX. I mean, after all, if it weren't for NASA's initial investment of nearly $400 million for the Falcon 9 and Dragon capsule, well then plus the multi-billion dollars for the CRS and commercial crew contracts, SpaceX most certainly wouldn't be where they are today. NASA does incredible things, vital research and science that no private company would or really ever could do. And they do a lot of behind the scenes things that can often go unnoticed. In my last video that compared SLS and Starship 2 years ago, back in the Tim inexplicably wore a high-altitude Russian flight suit in his bedroom days, I really drilled into why it's not fair to compare NASA, the organization, directly to SpaceX, the private company. As you probably know, in general, I'm Team Space, and I like to encourage my audience to fight tribalism and not just think one thing is the best and therefore everything else sucks. But when it comes to NASA building and operating a rocket, then we can properly compare the pros and the cons of those two systems. Because I already know there's plenty of you out there that are orange rocket bad, shiny rocket good, and vice versa. So let's come together, sing Kumbaya a little, and celebrate the fact that we have multiple mega rockets in existence. Yes. Okay, now that the hand-holding's out of the way, let's define the term super heavy lift launch vehicle, so you know why we're not including rockets like Blue Origin's upcoming New Glenn or other heavy lift launchers in this comparison. The aerospace industry considers a super heavy lift launcher as a rocket that can carry more than 50 tons into orbit. Super heavy lift launchers can of course put bigger things into orbit, but what that really means is having enough capability to potentially send large things to the moon or get probes on direct trajectories to our outer solar system without time-consuming gravity assists, potentially getting to outer solar system destinations almost 3 times faster. Historically, there's only been 5 super heavy lift launchers to ever fly, and only 4 of those were actually successful. They're the Saturn V, which could lift 140 tons, the Soviet Union's unsuccessful N1 that could have lifted 95 tons, then there's also the Soviet Union's twice-flown Energia rocket, which could fly 100 tons. SpaceX's Falcon Heavy technically can loft about 64 tons if SpaceX chose to expend all 3 boosters. Although this has never happened and may never happen, it does make Falcon Heavy technically a super heavy lift launch vehicle. Although when all 3 cores are reused, its payload capability is more like 30 tons. And lastly, the Space Shuttle, which if you include the orbiter as part of its payload capability, it could technically put 122.5 tons into orbit. Now we should probably point out real quick, by that same logic, if you included, say, the core stage of the SLS, which can get into orbit if they wanted it to, that would in that same way add another 80 tons to its payload capacity. But the shuttle was just a different beast, and you kind of in some ways had to factor in the orbiter as payload that went orbital, but the actual deployable payload capacity was really only about 27 tons. Although there was a proposed Shuttle C to make it super heavy, but okay, tangent. Let's keep going. So if humans are to return to the moon ASAP, or especially if we're going to get to Mars, we absolutely need to have some serious capabilities. Of course, I think we're long overdue for these kinds of missions. I want humans on the moon again in 4K. Well, actually, let's make it 8K. Let's just send MKBHD up there with some of his cameras. Now, before we get started with SLS and Starship facts, in case you've been living under a rock, we are currently working on getting back to the moon with NASA's Artemis program, and a substantial amount of work, funds, and goals have been laid out. So during this video, you're going to hear Artemis thrown around quite a bit. Although we could lump in the upcoming space station around the moon, Gateway, into Artemis, we're really just going to focus on the SLS rocket, the Orion capsule, and the human lander system. Which, to be clear, SLS is to Artemis as the Saturn V was to the Apollo program. And right now, the Gateway is being skipped for the first crewed lunar landing or two. And although a lot of things are drawn up and in progress for Gateway, we're just going to focus on the landing on the moon and the hardware that's directly involved in that. We're gonna set some records straight here before we pit these 2 rockets head to head, because I think a lot of people have the wrong idea when it comes to how and why NASA pursued SLS and Orion in the first place, and how they fit into the Artemis program. After the Space Shuttle Columbia tragedy, NASA started to rethink its next steps and began looking to a low Earth orbit replacement to the shuttle, and also started to set its sights on deep space exploration, and needed to build a big rocket in order to do so. NASA's original vision was the Constellation program, which would be a crew transportation replacement for the shuttle with the Ares 1 and a new deep space rocket called Ares 5. After slow progress and massive cost overruns pointed out in the 2009 Augustine Commission report, the Constellation program wound up being canceled. So the NASA Authorization Act of 2010 directed NASA to develop a space launch system, capable of lifting 70 to 100 tons to low Earth orbit and evolvable to 130 tons or more. The vehicle must be able to lift the Orion crew vehicle since its development was so far along and NASA was required to work with existing partners when available. As we know, NASA, instead of an Ares 1 low Earth orbit vehicle, ended up hiring commercial partners to send cargo and eventually crew to the ISS with the Commercial Crew Program, and NASA was tasked with a more focused and leaner rocket. The thought was to roll out a massive rocket quickly and efficiently, as their directive required the vehicle to be operational by December 31st, 2016. NASA performed a figures of merit analysis and narrowed it down to 5 different variations of a launch vehicle. Some of them were getting pretty exciting, with a 10-meter wide core diameter and oxygen-rich staged combustion engines. The analysis weighed the options of affordability being 55%, schedule 25%, performance 10%, and programmatic 10%. NASA landed on what we now know as the SLS. And although SLS and Ares 5 look very similar, SLS was technically a fairly blank slate design, but it definitely took cues from the rocket proposal called Direct, in which SLS would lean heavily on the literal leftover parts and facilities from the space shuttle as a quick and easy way to prototype and test out the most powerful rocket ever built. Unlike the Commercial Crew Program we know today, NASA would continue to work with the contractors from the shuttle using the familiar cost-plus contracting funding scheme, which basically means, here's how much money we're going to give you to get it done, but we'll also pick up the bill on anything that goes over budget. With funding hovering around $1.5 billion for SLS development per year since 2011, and the Orion capsule receiving a little more than $1 billion a year, the contractors were assured to have plenty of resources to make it happen, but while staying within a realistic NASA budget, which matched the funding levels during the shuttle era. But the problem with cost-plus contracting is it offers very little to no incentive to remain on budget or especially on schedule. In fact, timeline slips literally means more money for the contractors, and the prime contractor for SLS, Boeing, set to receive the most money for the project. Now, although NASA does performance reviews of their contractors, they've been scrutinized for being too easy on some of them. More on that later. So in order to keep some of these contractors, employees, and members of Congress happy, keeping the rocket's heritage close to the space shuttle ensured that funds would continue to be appropriated to shuttle contractors, or so the thought was. So although SLS does literally seem like a giant wingless space shuttle, it's really had many changes to make the vehicle have higher performance and lower costs than the space shuttle's parts. Here's a quick rundown on the changes. The SLS will have 5-segment solid rocket boosters as opposed to the 4-segment SRBs the space shuttle had, lacking any recovery hardware and featuring a redesigned plug that keeps squirrels and stuff out of it, with the redesign ensuring debris won't potentially damage the nearby RS-25 nozzles on ignition. The core stage, which although it looks like a space shuttle's external fuel tank, there's virtually nothing in common with the external fuel tank other than its color and its 8.4-meter diameter. It uses a new aluminum, Al2219, different construction and welding techniques, and even a different spray foam. People definitely tend to think it's literally a stretched external fuel tank, me included, but again, it shares almost nothing in common, mostly because SLS will have structural loads going down through the top of the tank as opposed to hanging off the side of the tank. The RS-25s have been tweaked quite a bit since the space shuttle and have increased their power output from 104.5% to 109% or 111% in an emergency. But again, just like the SRBs, the RS-25D and later the RS-25E variants will of course not be recovered on SLS. Just a fun side note, those percentage numbers are based on the original rated thrust of 1.6 meganewtons at sea level. After some tweaks in the space shuttle's main engines, they wound up being able to be throttled up beyond their original design during the shuttle's program and are being pushed even further with SLS. Another cost-saving and timeline-helping decision was to initially fly the SLS with quite literally the upper stage from ULA's Delta IV and Delta IV Heavy, known as the Delta Cryogenic Second Stage or DCSS. only it's been modified to fit on top of the 8.5 meter wide core stage, have different hydrogen tanks, and more reaction control fuel. This configuration is known as the Interim Cryogenic Propulsion Stage, or ICPS. SLS is intended to have a much more powerful upper stage known as the Exploration Upper Stage, which is considered to be part of the Block 1B upgrade and makes SLS much more capable. Next, we need to talk about the Orion capsule. It sits on top of this whole vehicle for the Artemis missions. The Orion capsule is a fairly traditional crew capsule and in some ways is a newer and embiggenated version of the Apollo capsule. But although it does look quite similar, it's a lot bigger than it might appear. At 5 meters wide versus the Apollo capsule's 3.9 meters wide and sporting an impressive 9 cubic meters of volume compared to 6.2 cubic meters, it'll be quite a bit roomier and capable of up to 6 astronauts. Although it'll probably only fly 4 for the Artemis missions versus Apollo's 3, which could technically fit 5. Well, barely. The Orion capsule used to be called the Crew Exploration Vehicle when it was in development for the Constellation program, but it has changed quite a bit and now features another cost-saving measure, which is a service module based on ESA's automated transfer vehicle. But one thing we need to mention that's still new to this whole lineup, and it's still in progress, and is definitely required for the Artemis program to land on the moon, and that is, of course, the actual lunar lander. And that brings us up to today. So far, everything we've talked about and discussed is only capable of getting humans into lunar orbit with SLS and Orion, because there really still isn't the capability to carry up a lunar lander with SLS Block 1 or even with the SLS Block 1B. But NASA has officially selected 3 very, very different lunar landers for the Artemis program, and each one has until 2021 to draw up exactly how they'll get their landers to the moon. You know, some proposals could actually wind up still sending modules alongside Orion in the upgraded Block 1B SLS. But to get to the moon for Artemis 3, which will use a Block 1 SLS, the lander will need to fly on a separate commercial rocket, or 2, or 3, or another SLS, depending on how big this thing ends up being, because Artemis hardware is big. This portion of Artemis is a lot closer to the commercial crew program than it is to SLS and Orion. NASA has just a set of requirements, but is letting the contractors put out proposals and doing so in a way that's incredibly quick and ambitious in the best attempt to get humans on the moon by 2024. NASA will not own and operate the spacecraft like they do for SLS and Orion. So this does mean that we will need at least 2 rockets per crewed mission to the moon for the Artemis program, likely even 3, maybe even 4. So we'll talk about the options the human lander system's proposals could use in the next video when we look at what other options NASA has if they just full-blown canceled SLS in favor of Starship and other commercial options. So let's talk about Starship. If you're new to the scene of Starship or SpaceX, you might not realize how far back this thing actually goes. Basically, since SpaceX started, there's been talks of doing a BFR or a Big Falcon rocket. And unlike SLS, the actual engineering and development had mostly been behind closed doors since the early days. And really, going back before SpaceX's start, propulsion engineer and employee number 1, Tom Mueller, had built a BFR rocket engine in his high-powered rocket club, Reaction Research Society, and yes, the naming scheme does come from Doom's BFG. Fun side note, Tom's BFR engine was a pintle injector engine that was targeting 10,000 pounds of thrust, and Tom was facing off against David Crisali, who built a more traditional flat-face injector. Tom's design won out, and eventually kind of became the basis for the Merlin engine. But the BFR vehicle didn't really gain any public notice until around 2012, when Elon would mention a huge rocket dubbed Mars Colonial Transporter that SpaceX would add to their lineup. But at this time, SpaceX was still a relatively small company, only having launched 3 Falcon 9s to date. After that, rumors were swirling about a Falcon X, a Falcon X Heavy, and Falcon XX rocket that would be their next mega rockets. It wouldn't be until 2016 at the International Aeronautical Congress in Guadalajara, Mexico, that the world would really get a sense for what SpaceX was actually working on. And yes, that was that super weird press conference where everyone asked ridiculous questions. Well, Not everyone.
Hello, Elon. Tim Dodd here, the Everyday Astronaut with Spaceflight Now. You show it going into orbit with the 100 passengers and then refueling it 3 to 5 times and then doing your Mars injection.
Right.
Is this the plan, or is it to have a fully fueled, IPT or MCT or whatever, and then put passengers on board? Or can you tell me a little bit about that process?
The plans Elon showed were properly ludicrous, maybe even plaid, something the world had never seen legitimately proposed. A fully reusable, 12-meter wide, 122-meter tall rocket with 42 full-flow stage combustion methane-powered rocket engines on its first stage. Then 6 vacuum engines and 3 more sea-level engines on the upper stage, an advanced carbon composite construction, and sporting a nutty 300-ton payload capacity. It was known as the Interplanetary Transportation System. After 2016, we saw some tweaks year to year, with the biggest change actually being an unbeginning change when suddenly the rocket shrunk to 9 meters in diameter, and the capability shrunk with it. Around this time, SpaceX started calling it BFR again and announced plans to send Japanese billionaire Yusaku Maezawa on a trip around the moon for Dear Moon. But maybe another big change was a decision to shift away from carbon composite construction and instead utilize stainless steel. Then the name Starship finally came into existence. And not to be confusing, the entire system is called Starship, but so is the upper stage on its own. The booster is called Super Heavy. So we can loosely say Starship, meaning Starship and Super Heavy, but we could also just be talking about the upper stage. Kind of like how you can point to corn and say, hey, look, that's corn. If it's off the cob and in a bowl, you'll still call it corn. But when it's on the cob, you might say it's corn on the cob. God, you can tell I'm from Iowa, can't you? In 2019, SpaceX held a press event in front of a full-size Starship mock-up prototype in Boca Chica, later known as Mark 1. By this point, the design was iterating less and less, and now the upper stage was to have only 2 fins that act like giant air brakes. Now, I already did a video explaining the reasons why they likely went from 2 fins instead of 3, and that's a fun video. But that pretty much gets us up to speed on Starship, since most of the development had been behind closed doors and on SpaceX's own terms. I think now would be a good time to go through the progress of these 2 programs, add up what exactly has been built, and see if we can get a better sense of their wildly different design philosophies. So this is a segment I've wanted to do for a while. Skeptics of Starship will point to all the blown up test articles and say, see, they can't even build a tank. While skeptics of SLS say, it's been a decade and nothing has happened. So let's lay out all the hardware that's been built. This will be pretty comprehensive, but not a full, complete list of absolutely everything. But we'll at least get out some of the major milestone things. Starting with SLS and Orion, there's quite a lot more hardware that's been completed and tested than you might think. So far, we've seen over a dozen Orions be used between Ares 1X, different abort tests, mock-ups, and drop test units. There's been a mostly feature-complete flight of a legit Orion capsule in 2014 on top of a Delta IV Heavy for EFT-1. I was at that mission and it was absolutely incredible. There's been a test of a full-size hydrogen tank of SLS that lasted over 5 hours at 260% of its structural rating at Marshall Space Center in 2019. All of the hardware for the first all-up test of SLS and Orion for the Artemis 1 mission is pretty much ready for final assembly. The core stage is currently on the test stand preparing to do a full duration static fire. The 5 segments of each SRB are ready to be stacked. The launch abort system is ready. The actual Orion capsule has finished all of its testing and is back at Kennedy Space Center awaiting its upcoming launch around the moon. The interim cryogenic propulsion stage has been ready to go for years. The Orion service module is ready. Literally, all of the hardware for Artemis 1 is completed and finishing up testing and then integrations. In total, there's 16 RS-25Ds, 4 of which are currently integrated onto the core stage, and 14 of those RS-25s previously flew on shuttle missions. There's enough solid rocket booster segments to make up 16 boosters. There's also 4 more RL-10 engines ready to be used for upper stages. And now that the manufacturing lines and practices are in place, Parts for Artemis 2 are coming together, including the LOX tank, hydrogen tank, inner tank, forward skirt, engine section, the pressure vessel for Orion, its service module, the heat shield, launch abort tower, and other bits of hardware too. And of course, as mentioned, the RS-25s and booster segments are complete too. But that's not all. Artemis 3 hardware is also coming together already too, including parts of Orion, the SLS hydrogen tank, parts of the service module, and again, the engines and solid rocket motors. This is what's been accomplished and completed throughout the last decade-ish. So how is that compared to Starship's progress? Starship's progress is very different. The Raptor engine started development around 2012, and since then, here's a list of what we've seen built and tested. To date, there's been over 26 Raptor engines built, many of which are in pieces now, and likely only a handful that are truly flight capable at this point. But that number is changing rapidly, as SpaceX has cranked out pretty much all of those in just 2019 alone. And if we ignore the progress and the test articles for anything carbon composite and or 12-meter diameter Starship, again, almost everything we're about to list was built within the last year. Starting with Starhopper, which is the only Starship prototype to really fly. Well, on purpose at least, with 2 flights. A 20-meter hop and a 150-meter hop. Then we saw the Mark 1 full-scale prototype come together. At the same time, SpaceX was building a similar prototype in Cocoa, Florida, as a way for 2 different teams to work on different methods of construction in a friendly competition. Mark 2, as it was known, has since been abandoned and is still just hanging out there. Then we saw the 2 teams come together at the end of 2019 to finish and test the Mark 1 prototype, which failed when testing, which was kind of expected because they were already working on the next one, which would be called serial number 1, and that's when they switched from the Mark to serial number nomenclature. There's been 3 subscale pressure test articles that have tested the welds and the ability to hold pressure at cryogenic temperatures around this time too. They tested serial number 1, which kind of imploded when its bottom fell off. Then we have serial number 3, which also failed due to improper testing procedures. And as of the making of this video, serial number 4 is already complete, and serial number 5 is well on its way. And if I keep trying to update this stupid animation with all the new parts they're making, this video will never come out because they're just making them so quickly. So in other words, SpaceX has built and blown up 3 times more tanks in the last 6 months than SLS has built in the last 6 years. And this is where we see the massive differences in the building, testing, and overall philosophies. Time to dig into this for a second. By now, you've already probably got a really good sense of the design differences and philosophies just by seeing how these 2 programs have developed over time. But there's a few things that really drill in just how different they truly are. So let's start by putting ourselves in NASA's shoes. NASA, being government funded, has to do things quite a lot differently than a private company with private funding. But perhaps the biggest thing they can't really do is take big risks. When building something as massive, complex, and ambitious as SLS, you really need to account for absolutely everything before you start sending out the instructions to the contractors. If you start telling contractors to start building something and then something changes in the plan, all of that work is for naught. And this compounds when you have dozens of contractors and government supporting employees all relying on each other to have their parts done on time. Imagine if a key part gets delayed a year. What are the government employees supporting that system supposed to do? You can't just lay them off for a year and then bring them back onto the project. They're gonna go find new work. You can't really reassign them to something else. It's not like a propulsion engineer is now just going to move over to the other rocket NASA is currently working on. There's a lot of inherent costs per year that are just simply sunk costs in running a program of this scale. So although it's inherently less risky and inefficient, there's also a safety net for having multiple contractors and space centers spread throughout the country, which massively helps make it more appealing to Congress. So although it is inefficient, it at least does help ensure the program's survival and that it continues to be funded. And this is especially true when you realize that it's been written into law that the upcoming Europa Clipper, a probe to Jupiter's moon, Europa, is legally mandated to fly on SLS. And perhaps most nutty about that fact is that $250 million has been added to the program because there won't be an SLS rocket until at least 2025, despite the probe being ready by 2023. But in the long run, this law did help keep a program moving forward and being funded during what could be very uncertain times with changing administrations. Now, this obviously isn't ideal at all, but if you're worried about your program's survivability and not just having your entire vision have to shift 180 degrees every 4 to 8 years, doing things like this is just kind of part of the game, for better or worse. But don't forget, NASA's budget is only about 0.5% of our national budget, and the human spaceflight programs aren't even half of that. So in general, the primary philosophy of building SLS is to plan ahead and take little risks, because there really isn't much room to fail when you have to answer to the taxpayers why their money literally went up in smoke. Now compare this to Starship. Starship development is literally about as blank slate as it gets. SpaceX started not with detailed blueprints, but quite literally started by just learning what questions to ask and how to frame the constraints of what their vehicle should do. SpaceX seems to have wound up with two main objectives: be fully and rapidly reusable, and have a capability large enough to be useful in getting humans onto other celestial bodies. That's really about it. And then start to work backwards. The next most pinned down item that helps to answer that question is developing an engine that is efficient and massively reusable. Like I talked about in my video about SpaceX's Raptor engine, a methane-powered full flow stage combustion cycle engine fits the needs of those goals perfectly. From there on, the whole thing is pretty much just a giant playground. Hence, when we saw that sudden and unexpected pivot from carbon fiber to stainless steel, you get a sense of just how important it is for SpaceX to just start flying so they have a starting point to iterate on when you hear Elon explain why it was so important to make the switch.
Taking the general approach of if a design is taking too long, the design is wrong. And therefore the design must be modified to accelerate progress. One of the most fundamental errors made in advanced development is to stick to a design even when it is very complicated, and to not strive to delete parts and processes. It's incredibly important. So this is why the switch to steel was because the advanced carbon fiber was taking too long.
This is why we're seeing so many random things happening down there at Boca Chica, Texas with the development of Starship. It's why it's kind of silly to even bother asking about future plans anymore, which of course, I'm as guilty of as anyone. Because everything depends on what's going to happen with the current step, and the step in development after that will be based on the results of the previous step, and etc., etc. It's a similar philosophy to something known as the Agile model, which is standard in software development, which makes sense because of Elon's original background in software. Basically, you don't work on step 2 until step 1 is done. Planning ahead any further, and you're very likely going to have to just undo work. Now this is quite literally the exact opposite of SLS, where everything needs to have an exact plan, because if you end up building the rocket 3 meters shorter than the blueprints, all of a sudden your entire ground support system will change too. And by the way, pretty much this exact thing has basically happened with SLS and its mobile launch tower. But everything for Starship is still on the table at the moment. I mean, we're literally seeing them build a factory around a rocket instead of vice versa. And frankly, this is pretty risky, but it's also much easier to do because SpaceX is so vertically integrated, meaning changes and decisions don't have nearly as big of a ripple effect as the other more traditional methods. But just know, we will see more hardware fail. We will see some setbacks. We will likely see explosions. But unlike SLS, not only is it okay to fail, it's halfway expected as a way to learn and prototype with lower costs and greater speed. Elon has said over and over in some way or another, failure is an option here. If things are not failing, you are not innovating enough. This is very similar to the Soviet Union's design philosophy. Basically, build something as cheap as possible, test it out. If it blows up, see what went wrong, make improvements, repeat. and it definitely gave them a leg up in the space race during early development. So say you blow up a rocket that you built in a month. Oh well, learn from it. SpaceX will build another rocket in less time than it'll take NASA to fuel up and test fire the SLS once. And that's just simply a huge, huge difference in philosophies. Okay, I think it's time we really stack these rockets up side by side to help figure out just how they really compare when we look at their nuts and bolts. We've already touched on each vehicle's dimensions, so here they are again on screen. For now, we'll just compare some initial builds of each rocket, so the Block 1 and Block 1B of SLS, and the roughish version of Starship as it currently stands. But definitely keep in mind that Starship will change a lot, pretty much every time one gets built for the first dozen or two, but SLS could also change quite a bit too if Block 1B goes online. But while we're at it, let's throw up the Saturn V and the Falcon Heavy, just so we have some extra perspective on how these vehicles really compare. As they stand today, SLS is big, really big, but Starship will be huge. Now let's talk engines and their fuels. Falcon Heavy has 27 sea-level Merlin engines and a single vacuum-optimized Merlin engine on its upper stage, which all run on RP1. Then there's the Saturn V, which had 5 F1 engines on its first stage that ran on RP1, 5 J2 engines on the second stage, and a J2 engine on the third stage that ran on hydrogen. As we know, SLS has 2 SRBs, 4 RS-25s running on hydrogen, and the Block 1 has only a single RL-10B2 on its upper stage, and the Block 1B will have 4 RL-10s that all run on hydrogen. Lastly, Starship has 37 engines on its Super Heavy booster, and 6-ish Raptor on Starship. This number is very subject to change, and it's relatively easy for SpaceX to do so because of the small size of the Raptor engine. Next, let's take a look at their thrust at liftoff. As always, this is pretty fun. The Falcon Heavy is the baby here at 22.8 meganewtons, followed by the mighty Saturn V at 35.1, then the SLS at 39.1, and lastly, Starship will be the king here at 72 meganewtons as it currently stands. Now we've already gone over some of these rockets' low Earth orbit capabilities, so let's add SLS and Starship back into this. Now notice we are going to be showing performance for SLS Block 1 and the Block 1B upgrade, but their low Earth orbit capabilities are virtually the same since it's the core stage that pretty much drops them off into orbit. But now, let's show how much mass they can shoot off to the moon, otherwise known as a translunar injection or TLI, since we're talking about lunar missions here anyway. Quick note, this isn't necessarily how much a vehicle can put into lunar orbit, just how much it could shoot off to the moon. You still need to get into lunar orbit with your spacecraft. In the case of Orion or Apollo, that's done with the service module. And this is technically a C3 of minus 0.99 to be exact, which is the measurement of the characteristic energy to get to a certain point in space. Falcon Heavy, when reused, can sling about 9 tons to the moon if all 3 cores land downrange on drone ships, or about 15 tons when expended. Then we have the Saturn V that could send 48.6 tons to the moon. Then SLS Block 1 can take 27.5 tons, and the 1B version can take up to 43 tons. Now you might ask, how can a more powerful rocket get less to the moon than the Saturn V? Well, that interim cryogenic propulsion stage is seriously undersized for the size of rocket. But oddly, even with the Block 1B and the 4 RL-10 powered exploration upper stage, the SLS can still only send 43 tons to the moon, so that's shy of what the Saturn V was capable of, which, quite frankly, that's kind of baffling to me. And Starship is a little more confusing when it comes to TLI. Starship on its own cannot do a translunar injection. Because of its massive 120-ton dry mass, lugging all that dead weight all the way out to the moon doesn't work out without it being refueled. Now, of course, in-orbit refueling is 100% part of the plan for Starship. But we'll talk about that more in an upcoming video where I'm going to talk about Starship using a kick stage versus Starship refueling. So now here's where we're going to go into a deep, deep rabbit hole. So hold on to your butts. We're going to talk price. And this is not an easy thing to talk about. You'll see why. And all these numbers you're about to see are adjusted for 2020 US dollars. Let's start off with what I'm going to call the sticker price. This is the price you could presumably buy a launch For now, we're kind of ignoring development costs and just what the invoice would be for the launch of said rocket. But we're going to get into the development costs in just a second, but for now, just file these away. And we're also going to look at just the rockets, not the spacecraft like Apollo or Orion. Starting with Falcon Heavy at around 90 million when reused and probably around 150 million when expended. The Saturn V was around 1.2 billion, SLS Block 1 and the later Block 1B will be 875 million once production stabilizes, and Starship, well, Elon claims they can launch for 2 million, but let's assume they can do 2 million, but for a while they'd be smart to charge 100 million until the market catches up. So let's just throw 100 million out there as more of a worst case scenario sticker price. Now with these numbers, we can do a very baseline dollar to kilogram ratio, and since we're talking about the moon again, let's only look at how much it costs to send 1 kilogram to the moon on a translunar injection for each of these vehicles. Falcon Heavy can get 1 kilogram to the moon for around $10,000, whether it's reused or expended. Then the Saturn V was about $25,600. SLS Block 1, best case scenario with a stabilized production, is around $31,500, but Block 1B looks quite a bit better at $20,000 per kilogram. And lastly, Starship. Now remember, a single $100 million Starship launch can't get anything on a translunar injection. So it's going to take 2 additional launches to refuel it at an extra $100 million each in order to send 156 tons of payload on a translunar injection, which would wind up costing around $2,000 per kilogram. In case you couldn't tell, we're kind of sandbagging Starship just in case it's way too optimistic. And even so, it's still by far the most economical thing on the chart. But these preliminary costs are taking a lot of assumptions. They don't really factor in development costs, and we've still got a lot to cover on the topic of budgets and costs. So for now, just file this away, because in the next video, we'll really chase all the rabbit holes when it comes to costs. So, how did we get here? How is it that we have 2 completely different, super duper mega rockets going online at the same time? I think the history kind of speaks for itself. When NASA started working on SLS, the thought of a rocket like Starship would have been utterly ludicrous. I mean, even today, many people think it's insane and likely to fail, but Starship is impossible until it's not. And then all of a sudden, literally everything changes. And don't forget, NASA has been working on SLS and Orion for nearly a decade. If SpaceX had approached NASA with the idea of Starship in 2011, it would have been like trying to sell a farmer in 1870 a GPS-guided 9-liter turbo diesel-powered 4-track 8RX 410 John Deere tractor with an infinitely variable transmission, an 85cc displacement integrated hydraulic pump with 227 liters per minute of hydraulic flow, air-conditioned and heated, 10-inch touchscreen displays, and digital monitoring when they were looking to purchase a plow for their horse. They just simply wouldn't have believed you. Oh man, I showed my Iowa again. Sorry. And NASA has had the rug pulled out from underneath them so many times, so many programs getting started, only to change direction and change hands 100 times before the program even has a chance to really get going. So NASA did what they had to do. They took a safe, conservative route, leaning on existing technologies, partners, and program funding schemes to lay out a rocket that would, for better or worse, have a hard time being canceled, so they could at least have truly deep space capabilities for the first time in nearly 50 years. Because I think that's the biggest shocker in all this. It's not Starship. Humanity has Starship coming. Starship is destined because frankly, it makes sense to build a fully reusable rocket. Everyone wants that. Everyone wants to do that. No one thinks that's a bad idea, and no one thinks it's never, ever going to happen. But I think the biggest surprise is that it would be almost 50 years before there was a rocket capable of taking humans to the moon after the Saturn V. If you told that fact to the last person to walk on the moon, Gene Cernan, upon his return home in 1972, that no one will have returned to the moon by 2020, he probably would have pulled a Buzz Aldrin and punched you right in the face. It wasn't until the market shifted that rocket technology became achievable not by nations, but by a small handful of brilliant and plucky individuals that could rethink everything and open up commercial options and opportunities that just simply didn't exist before. I know Elon's life goal is to get to Mars, but in the meantime, he'll have completely changed humanity's access to space for the better. And yes, even when you factor in how much rockets pollute, because trust me, I've already done a very, very long video on that too, which is a fascinating topic. You should definitely have a watch. In order to get to Mars, you need a fully reusable, massively capable rocket, and come to find out that insane proposition just so happens to completely shift the economics of spaceflight by orders of magnitude. I mean, the reason we stopped going to the moon in the first place was because it was so expensive, and the United States had clearly measured their genitalia against the Soviet Union, and that just simply wasn't a sustainable way to explore the moon. So speaking of sustainable ways to explore the moon, that's what we'll really dive into in my next video that by happenstance is mostly done already. So stand by and we'll answer, should NASA just cancel SLS and use Starship and other commercial launchers? So at the end of the day, in my opinion, orange rocket, good enough for now. Shiny rocket, incredible for the very near future. And we as Team Space can celebrate the fact that we live at a time where we get to have two super mega rockets go online at roughly the same time. Yes. So what do you think? Did you learn anything new? Did any of your perspectives change? I know mine did. Honestly, when I started making this video and working on the script, I thought it was a foregone conclusion. I thought that I thought I knew everything, and come to find out it was actually pretty humbling to really go through how all this stuff works and just kind of do a reality check for myself. So let me know if you learned anything or something shifted in your mind. And I'm sure the comments are already still full of SLS versus Starship, which is kind of what this video is about. And I'm probably guessing that I really didn't help to reduce the number of Twitter arguments. Sorry, Joe Barnard. I have a quick list of people I need to thank for helping with this video. First off, Boca Chica Mary and NASA Spaceflight for providing some of these wonderful images of Starship development. I'm sure you're already following them, but in case you haven't, get your butt over there and follow their work. Then I need to thank Kimi Telviti, Casper Stanley, and Martian Days, who all have helped provide some of the beautiful renders you've seen. So definitely shoot them a follow. But also thanks to Declan Murphy from flightclub.io for helping me come up with some of these numbers and crunching some stuff. He started working on a yeet calculator, which is just awesome, thanks to some of the stuff we were working on, trying to figure out which rockets could do what things. So definitely check out flightclub.io and check out his Patreon page if you want to help him do the awesome work he's doing. Speaking of Patreon, I definitely owe a huge thank you to my Patreon supporters who've already heard this video so many times before it comes out. They fact check and do a lot of work for me on the back end, and it's just awesome. We have such an incredible community. So thank you guys for all your help. If you want to help, add your voice, your opinion, do some fact checking, or just hang out with like-minded space people, definitely consider becoming a Patreon supporter where you'll gain access to our exclusive subreddit, our exclusive Discord channel, and exclusive monthly live streams. That's patreon.com/everydayastronaut. Thank you. And while you're online, be sure and check out my web store because we have really cool merchandise like this lunar mission shirt, which, by the way, you didn't even get to see the back yet. Check this out. Now there's actually a little Easter egg here to this t-shirt. So notice it says lunar mission in this photograph, but there's actually more to this photograph. So if you can figure it out, if you can figure out what else is there besides lunar mission, not the remove shoes before entering cabin, but the additional words to lunar mission. If you can figure out what the rest of that says, go ahead and type that in at checkout for a coupon code and you'll get 10% off this t-shirt. So good luck. We have really cool merchandise. They're all hand printed here in the United States, hand sewn on patches. We're constantly making new stuff. Get ready, there's going to be a lot of really cool new things, so check back often because some of the stuff is so cool that even Elon Musk wears it. Seriously. That's everydayastronaut.com/shop. Thanks everybody, that's gonna do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.